Okay, welcome back to the channel. I'm your strategist, and today we are flying at maximum altitude. We're diving straight into a masterclass on one of the most critical areas of the Cambridge 0580 mathematics syllabus, geometric constructions and nets. Look, we see two types of students tackle these exam questions. You've got students like Alex who overload their brains with raw mathematical facts but completely lack the spatial analysis to apply them. And then you have students like Sam. Sam rushes the paper, misses the exact requirements of the command words, and throws away easy marks on a sloppy protractor reading. Today, we're fixing all of that. We are taking geometry off the flat textbook page and turning it into a dynamic, high-scoring exam strategy. Whether you're taking the O-level or IGCSE, you're in the exact right place.
So picture this. How do you actually turn a flat, two-dimensional piece of paper into a perfect 3D box in your mind? It sounds a bit like a magic trick, right? But the truth is, the examiners are specifically testing your tactical, step-by-step process of spatial reasoning. They want to see if you can decode the command words and build, measure, and visualize complex shapes from the ground up without second-guessing yourself. By the end of this explainer, you won't just look at shapes on a page. You are going to understand their underlying anatomy, and more importantly, you'll know exactly how to extract maximum marks from them. Here is our flight plan for today's session. 1. The art of measuring angles. 2. Constructing triangles with compasses. 3. Visualizing 3D shapes from nets. And finally, 4. Extracting area and volume from nets.
Let's move into Section 1, the art of measuring angles.
We're starting with the absolute cornerstone of geometry, achieving pinpoint accuracy when you measure. Listen, if your angles are off by even 2 degrees, your entire construction falls apart and the examiner pulls out the red pen. So before you even pick up your measuring tool, there is an absolutely critical preliminary step that top-tier students do instinctively. You need to look at the angle and guess its size. Seriously, just make an estimate. Is it an acute angle, less than 90 degrees? Or is it obtuse, sitting somewhere between 90 and 180 degrees? Taking 2 seconds to establish a rough estimate before you even touch that protractor is literally your best defense against the most common exam room errors. It's a reality check for your brain.
Now, take a really close look at this setup. This perfectly illustrates the #1 mistake we see students make on past papers: reading the wrong scale. Protractors have an inner and an outer scale, which is basically a trap waiting to be sprung if you're rushing. But look at the alignment here. By placing the crosshair of the protractor perfectly on the vertex of the angle and making absolutely sure the 0 line sits flush with one arm, the path is crystal clear. You have to start at 0. Follow the scale that actually begins at 0 until you hit the other arm. In this case, following that inner scale from 0 takes us precisely to 117 degrees. Think about it. If you hadn't done your mental estimate first, you might have panicked, read the outer scale, and written down 63 degrees.
Before we continue, subscribe to our YouTube channel, Ace the Exams, at Ace the Exams IGCSE, to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Okay, so that technique is flawless for angles up to 180 degrees. But what's your strategy when the exam throws a massive reflex angle at you, an angle bending all the way backwards, between 180 and 360 degrees? Since standard exam protractors are semicircular and max out at 180, you can't just measure a giant reflex angle directly. The strategy here is a quick 2-step calculation. Step 1. You measure the smaller hidden angle on the inside. Step 2. You subtract that exact number from a full 360 degrees. It's a guaranteed full-mark method. Let's see this strategy in action. Look at angle A right here. The command word says calculate the reflex angle. So we flip our thinking. We place the protractor on the inside of the arms and measure the acute angle instead. Following our 0 scale rule, we find it locks in perfectly at 53 degrees. Since we know a full rotation is exactly 360 degrees, we set up our evidence for the examiner. We write down 360, subtract our inside measurement of 53, and boom, we've perfectly calculated the outer reflex angle as 307 degrees. This is how you show you're working and secure the points.
All right, moving right along to Section 2, constructing triangles with compasses.
Now we're upgrading from just measuring lines to actually engineering perfect geometric figures from scratch. Welcome to high-stakes geometrical constructions. If you want maximum marks, there are strict rules of engagement. You use a ruler for straight lines. Your accuracy must be within 1 millimeter for lines and 1 degree for angles. But I want you to focus on that middle bullet point. It is absolutely crucial. Leave in all construction arcs. Students like Sam always try to make their paper look neat by erasing those faint compass sweeps. Do not do this. Those arcs are your evidence. They are the mathematical proof that you actually constructed the shape rather than just sketching it. Without them, you get 0 marks.
Let's break down the mechanics. Imagine the paper asks you to construct a triangle with sides of 5, 4, and 3 centimeters. First, you lay down your 5-centimeter baseline from point A to B. Then, the compass takes control. You stick the sharp metal point firmly at A, open the pencil arm out to exactly 3 centimeters on your ruler, and draw a smooth, sweeping arc above the line. Next, move the sharp point to B, set the compass width to 4 centimeters, and strike a second arc. That exact spot where those 2 sweeping lines intersect, that is the undeniable, mathematically perfect location of vertex C.
But wait, before you dive in and execute that flawless intersection, there is a secret weapon that top-tier students use. Always, and I mean always, draw a quick rough sketch in the margin before committing to the exact 1 millimeter precise construction. Your rough sketch acts as your blueprint. It organizes your spatial awareness so that when you pick up the compass, you already know exactly where those arcs are supposed to cross. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Once you've got this intersecting arc technique locked down, you can construct literally any triangle the exam throws at you. Need to build an equilateral triangle where every side is exactly 4.2 centimeters? Easy. Or an isosceles triangle with a base of 5 and sides of 6? No problem at all. Your compass doesn't care about the complexity. It flawlessly engineers these structures using nothing but those core lengths. You anchor the point, you sweep the arc, you find the intersection, and you draw your lines. It's a guaranteed win every single time.
Let's shift gears. Section 3. Visualizing 3D shapes from nets.
Okay, it's time for a serious mental workout. We are transitioning from flat 2D lines into the 3D world. We're talking faces, vertices, and volumes. But before we get ahead of ourselves, what exactly is a net? Imagine taking a standard cardboard shipping box, taking a knife, cutting down its edges, and laying the whole thing completely flat on the floor. That flattened, two-dimensional shape is the net. It's the unwrapped skin of a 3D object. The exam will test your ability to predict exactly how these flat patterns fold back up into solid objects, which requires some serious spatial awareness.
So, let's do a quick visual challenge. Look at the screen right now. On the left, we have the net of a regular triangular-based pyramid. It looks like one massive triangle that's been divided into 4 smaller, perfectly identical triangles. Now, do the mental gymnastics. Picture grabbing those 3 outer points with your fingers and folding them up toward the ceiling. Can you see it? They meet perfectly in the dead center, forming the sharp tip of the 3D pyramid shown on the right. That is exactly what your brain needs to be doing during the exam.
But let's look at a shape you'll see all the time, the cuboid. Basically a shoebox. A cuboid has 6 distinct rectangular faces. So logically, its flat net needs exactly 6 rectangles. But here is the ultimate trap question. Does every random arrangement of 6 rectangles automatically fold together to make a working box? If you just slap 6 rectangles onto grid paper, is it guaranteed to form a 3D shape? Take a second to really think about that.
If you said no, you are absolutely right. The examiner loves to test this. Look at these specific grid examples. Some of these arrangements fold up beautifully, while others are complete structural failures. Check out shapes A and B. Thanks to their cross-like layout, those outer flaps will fold up, create the walls, and seal the box perfectly. But look closely at shape C. Yes, it has 6 rectangles, but if you actually try to fold it in your head, those bottom rectangles are going to fold straight into each other. They'll overlap completely, and you'll be left staring at a massive, gaping hole on the opposite side of your box. Spotting these flaws without physically touching the paper is exactly how you jump up a grade boundary.
Which brings us to our final strategy, Section 4, Area and Volume from Nets. We are bringing it all together now. We're going to extract cold, hard, measurable data from these mental models. The absolute best strategy for decoding a net is to anchor it to a physical grid. When you lay a cuboid's net onto a 1 centimeter square grid, its dimensions are fully exposed. We can easily count the squares and see that the main central rectangle is exactly 3 centimeters long and 2 centimeters wide. The side flaps are exactly 1 centimeter tall. Immediately, before we even fold it, we know our core dimensions. This is going to be a box that is 3 by 2 by 1 centimeters.
And the second you have those dimensions decoded, calculating the total surface area is a breeze. Surface area is literally just the total area of the flat cardboard net. We structure our calculation by systematically working through the face pairs. Because opposite faces on a regular cuboid are completely identical, we just group them up. The top and bottom are both 3 by 2, giving us an area of 6 each, so that's 12 square centimeters. The front and back are 3 by 1, which totals 6, and the two sides are 2 by 1, totaling 4. We simply sum up all those individual parts, and we get a grand total of 22 square centimeters. Write it down clearly, state your units, and collect your marks.
So that covers the outside skin, but what about the actual capacity inside the box? Volume is remarkably straightforward once your net is decoded. You just take those 3 core dimensions we found, the length of 3, the width of 2, and the height of 1, and you multiply them. 3 times 2 times 1 equals exactly 6 cubic centimeters. Think about how powerful that is. You just calculated the internal 3D volume of a shape simply by analyzing a flat 2D drawing on a piece of paper.
Let's run a quick real-world challenge to finish up. Imagine the exam question asks for the net of a box to hold paper on a desk. The base is 15 by 20 centimeters and the height is 5 centimeters. But here is the trick. The command text specifically says it's an open-topped box. If you aren't paying attention, you'll draw 6 rectangles and lose the mark. To draw this correct net, you actually have to remove the top rectangle from your mental model. You just draw the base and the 4 walls. It's a brilliant test of whether you're blindly memorizing shapes or actually adapting your strategy to the specific constraints of the question.
And that kind of spatial manipulation is exactly what separates the top students from the rest. Honestly, if you ever struggle with nets, grab some grid paper, physically cut a complex shape out, and fold it yourself. Seeing where it overlaps in real life will permanently rewire your brain for the exam. Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at Ace the Exams IGCSE to excel in your Cambridge examinations. Subscribe right now to Ace the Exams IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here. Keep analyzing, keep constructing, and I'll see you in the next session.